This module focuses, we begin with stability and vertical motion. The two are very much related, and they're also unrelated. So let's see if we can talk a little bit about that. Vertical motion. An air parcel, any parcel of air, moves in three dimensions, horizontally and vertically. So that vertical component of the air has big influences on you as a pilot, on the weather that occurs. So we got to understand that vertical motion part in order to understand how your flight's going to go, what kind of weather you might have. So we'll talk a little bit about that. Why does air move up? What causes it to move up? And then why might it accelerate faster? And that's where it's related to stability. Depending on the atmospheric stability, that air parcel might pick up speed and start accelerating upward, or might just lag along very slowly, working its way up or down. And maybe the stability will push that same air parcel downward. So we're going to talk a little bit about that right now. One of the things to look at here is convergence and divergence. All right. Here I have a high pressure system centered north of Maine. Winds are out of the northeast coming in here. I have a low pressure system centered over southwest of West Virginia. I have south winds coming up here. Okay, somewhere in here I probably have a warm front. So I have a low with a warm front in here. Notice how the winds are coming together right here. They're coming up from the south, and they're coming in from the northeast, and they're merging, getting together right in this area, right along this line. And this coloring is 6-hour precipitation amounts. The bluer is the heavier precipitation. Well, that's where the air is coming together. That's convergence. The air is hitting each other right there, and it's being forced to rise. So if you see south winds and a north wind coming together along a frontal boundary typically, you know there's going to be rising air there. Same thing's holding probably down here. You got pretty strong northwest winds, and then the winds shift to the southwest right here. Well, the stronger winds are going to blow into these slower winds, that air parcel, and there's going to have to be some air that gets pushed upwards along this boundary right here. That's the cold front right there, dripping on down into Florida there. So you can see that these stronger winds pushing in are causing the slower winds get overtaken, forcing them to rise. So there's your convergence. One other thing that might cause air to rise is topography. And West Virginia does have mountain ranges. So let's think about that. If I am pushing winds in from the east into West Virginia mountains, they got to go up, and then they go down on the other side. Notice over here it's really drier. And while that's partly due to the cold front getting through, but it's also partly due to the fact that the winds are being pushed downward there by the Appalachian Mountains. Are going down the other side of the Appalachians. So a lot of times in West Virginia, if you have east winds, you get a lot of rain on the east slopes of the mountains and not nearly as much on the west slopes. The same is going to hold true in the Rocky Mountains, especially out there. If you think about it, you get some tremendous rainfalls in the Sierra Nevada sometimes where the winds are coming in off the Pacific. But if you go right on the other side of the Sierra Nevadas, you get like a rain shadow. It's just stopping it dead right there. So this is just a little bit about that. One of the things about atmospheric stability is it can really increase the velocity of the air going upwards. So in order to look just a little bit at this, we'll look a little bit first at today's weather. We talk about convergence. Wow, look over here in Minnesota. And right now there are thunderstorms and showers going on in Minnesota. We'll look at this. You got south winds here, southeast winds almost, coming in towards that frontal boundary, and here you have north winds. You would guess that there's pretty strong convergence right in that area right now. So, and here you have the cold air to the north. Not a really strong cold front, but not moving very much yet. And typically by this time of year, I would have thought a cold front like this would be barreling southeast, but it's not yet. So I'm not complaining. I got warm weather here yet. Here's left of Florence down here, tropical storm at this time, winds all around it. One of the things too with low pressure, the winds are always circling in towards the center of low pressure, so there's always convergence because they're circling towards each other, towards the middle. Whereas high pressure, the winds are tending to go outward, away from the high, clockwise. So there's a difference there. There's divergence, which is downward motion, and convergence around the high, around the low, which is rising motion. So let's see if we can look at a sounding and look at just a little bit at stability. Air is going to cool as it goes up. Air cools for a reason. Here's a diagram of stability here with the convergence at the surface, or divergence at the surface, and you see the air is going down. You can see the same thing is kind of happen at the jet stream level, aloft. You may get a lot of convergence or divergence there. And we're going to look at jets in a minute here to try to explain that a little better. One other picture I wanted to show you through here. We'll go over to it quickly. You can see the mountain ranges and it's all there too, which showed the vertical motion. And I think that's really what I wanted to look at there. Let's just go back to the sounding here a minute. Okay. First thing you got to know is the temperature, if it's completely dry air parcel, and notice we haven't talked about moisture at all yet. So let's just say we have dry air. The temperature is going to cool at the rate of 9.8 degrees Celsius per 1,000 meters. Okay. So if you go up a little bit over 3,000 feet in the atmosphere, you can expect that temperature to cool 9.8 degrees approximately over that distance. All right, this is a skew-T diagram. And I know you probably aren't caring a whole lot about soundings and all, but I think they're valuable, and I think you're going to find them useful. Skew-T means the temperatures go up to the right. They're skewed. It's a skew-T. Pressure is off to the left, 1,000 millibars, 850, 700. And there's some estimates based on a standard atmosphere in kilometers of how high you are in the atmosphere. So here's 500 millibars. Notice the distance between 7 and 500 has expanded. Well, the scale over here is such that it kind of mimics what happens in the atmosphere. 850 and 1,000 are very close to each other, and 850 to 700 is pretty close. And then you get a little bit further apart between 7 and 5, and even further between 5 and 3. You can see the distance is expanded here. Look at the distance in 2 and 3 kilometers distance here almost between these two. Whereas down here, less than 2 kilometers for 150 millibars versus 100 millibars there. And you can see here it's probably up close to 20 kilometers up here. So they really spread apart. So now looking at these, this is a sounding. The sounding is an atmosphere taken by a balloon. And as it's going up, it has a temperature gauge on and an instrument hanging below it. Temperature is plotted in red on these. So at this elevation, this is the temperature. Well, approximately maybe a little bit over 10 degrees Celsius. Look over here, plotted in red. It's 0 degrees Celsius. So from this point to this point, the temperature changed almost 10 degrees over that distance. So you can see that here's almost dry adiabatic lapse rate, probably right in here. And you'll notice there's a dashed line, little dotted line right there along it. That is the dry adiabatic lapse rate. They plot them on these as they see it sometimes. So you can see here this temperature is cooling pretty quickly. If you had an air parcel that's temperature was over here, for whatever reason, and I'm not going to explain why right at the moment, that air parcel is warmer than this. Think of a hot air balloon. If you got a hot air balloon, it rises. Well, that air parcel is going to want to accelerate upwards. It wants to go quickly. So that is where it's happening with stability here. If the air parcel is warmer than its surrounding atmosphere, it's going to want to go up. If it's colder, it's going to want to sink like a lead balloon right back down towards the earth. Now, take into account what you have with your vertical motions, just from things like convergence and divergence. If you have unstable air, and the more unstable, the faster that acceleration upward. And I'm calling it acceleration because it's literally getting faster and faster as it's going upwards. That acceleration is going to push that air parcel, that velocity upwards that much quicker, and you're going to get tremendous vertical motion there. However, if that air parcel is over here and it's colder than the sounding, then it's going to go sinking back down. You'll notice this sounding has all kinds of variations in how the temperature goes up, because all soundings have that. I know a lot of planes are now equipped with, I forget that exact acronym for it, but I've looked at this. They produce a sounding as they take off. They produce an air temperature as they're traveling along. Those soundings would picture on a diagram like this, would show exactly the same way. So one last thing I wanted to look at on this one, though, is I want to look aloft, and we're going to look upstairs. And we're going to, instead of looking at, we're going to look at up an air chart. I want to look at divergence today. And divergence is usually a good space to try to find divergence and convergence on a jet stream. Notice here, very, very fast wind. That's your jet. It's a jet streak, actually. The jet is this whole big area of fast winds. But you look for the concentrated, smaller areas. That's a jet streak. All right, well, now let's take that into account. If you're moving along like that, your air up here is going 110 mile an hour, 120. Up here, it's only going 80. You got some kind of convergence going up here. You got sinking motion. Back here, it's accelerating into it, and you have rising motion. So you can see there's actually changes going on around the jet that's going to produce rising and sinking motion. So say you have sinking motion aloft, and underneath it you have low pressure with rising motion. That rising air is going to be slowed down as it's going up. It's not going to go up real fast. So it's not really going to get really a good vertical velocity there. But if you have divergence aloft and then you have convergence at the surface, you want to couple it like that, you wind up with faster and faster rising motion. So this is just a little bit about vertical motions, how they can happen, and stability and how that impacts what the vertical motion will do.